Yeah, good evening guys. So please type in the chat box, is the audio and video clear to all of you? Good evening, hi all of you. Please type in the chat box, is the audio and video going fine? Yeah, fine, great. Okay, so let's start. So basically we are supposed to start this single variable calculus in yesterday's class, but of course unfortunately we had got a technical snag and we have to push it to today. Okay, so anyway I'll welcome you back all onto this series of 7 p.m. every day that we have started engineering mathematics initially, and we have started with basically we have started with which chapter? Linear algebra, right? Yeah, correct. So we have started with linear algebra, then we have seen what is a matrix, then types of matrices, okay, and then after we have gone through a lot of things basically, okay, concept of rank, nullity, okay, nullity is nothing but the null space, okay, so the dimension of the matrix minus rank of the matrix actually, and then we have talked about vector spaces, subspaces, then linear combination of vectors, okay, then eigenvalues, eigenvectors, then diagonalization is again one important concept which we have gone through, okay, then we have seen certain of course determinants and all, some basic discussion we have got, and definitely we have moved on to solving methods, okay, basically we have solved to we have solved LU decompositions, okay, Gauss Seidel and Gauss eliminations, all these things we have done, correct? Both Baya laga hi ho sir. But yeah, okay, fine, thank you. So today is my first class. Any pay requirement? No need. Okay, Baba, just continue attending the class. Clear? So in today's class, we will start the completely new module, single variable calculus. Okay, so it's really very important. Whatever the branch you choose, of course, in engineering we keep optimizing things. Okay, let's say for example, if I design a microprocessor, for example, okay, and let's say I'm interested in producing the microprocessor such that its lifetime is maximum, for example, okay, so we'll collect some data. Let's say for example, if I generate for, let's say for one company I have generated microprocessor and I have taken data, okay, so on an average how many days or how many years basically this microprocessor is working, then using my skills and using my techniques I'll try to change certain parameters during its manufacturing and I'll try to maximize the life of it, correct? And ultimately if I have the maximum life, it will gain me a lot of productivity. So again, this optimization is one very crucial thing which we keep doing many times, of course, and not only that, in calculating a lot of geometrical aspects, okay, in identifying many technical stuff, this calculus is very much useful, okay. In fact, calculus when put together with trigonometry, it's like a massive thing, okay, like if you solve projectile equation, okay, many of you might have studied projectile equation. Have you studied projectile equation? Very nice chapter in your maybe class 11, I guess. Yeah, and if people are doing with mechanical or civil, it comes in engineering mechanics. Hi Ashwini, good evening. Have you ever studied projectile motion? Projectile, in class 11 I think there's an important question. The path of show that the path of a projectile is parabola, okay, they'll ask you this question. They'll ask you to show the path of a projectile is parabola and you'll do some derivation and all, correct? So anyway, coming to this calculus holds a very big reason, of course, and of course to get more updates anything on this channel, please follow the Telegram links, okay. So that thing onto the right side of me is basically my this English Wallah channel, Gate Wallah English channel, so that if you have any update on this channel, any upcoming events or any video that's getting posted, okay, so it will be quickly notified here so that your time gets saved a lot. Good evening all of you, welcome. Okay, and this is my personal channel, so me and my PW students together will actually maintain this. So if you have any interaction, or if you want to interact with me, or if you feel I can help you at some point, maybe technically or somewhere in guidance point of view, you can definitely follow this. I'll be keeping my updates, or if anything is there that I need to say something, I'll post it here so that you can get enough information about the things. Anything that's related to the Gate Wallah English channel will be posted in this Telegram channel. So if you can scan this, it will direct you to a link of that group, so you can join directly, okay. And this is mine. And now if you see this feature, we have recently launched Unity. So this Unity, if you just type Unity PW in Google, okay, the first link if you open, it will ask you for a sign up. The only thing you have to do is, once you sign in and you have your account, it's for free, nothing cost and all. So you'll see whenever you're typing comments, if you have any doubt, before you type your doubt in the chat box, like in the YouTube chat, you can use exclamation doubt and then start typing your doubt. Like let's say if I ask you what is a limit, okay, then if you have the same doubt, if you type before start typing what is a limit, if you do this exclamation doubt and then if you type what is a limit, they all get stored in a one particular place, okay. So it doesn't matter how many YouTube sessions you attend in a year, or basically how many sessions you attend or how many doubts you ask, everything will be recorded at one particular place. Similarly, this Unity has also the feature of note saving. So if you want to make any important point, okay, if you want to save your important points at one place, then you can type exclamation note, and then you can type the point, then definitely that point will also get stored. Okay, and there's a track record of total how many polls, because during the live classes I keep attempting basically keep connecting polls, which you might have seen generally. So we'll keep connecting these polls. So if you keep participating in polls, you'll have a track record. Clear? Unity is also for paid batches. Yeah, we have launched it. Okay, so anyway, let's see. Now in the last lecture, so basically in the last lecture we have made a conclusion roughly of linear algebra. Only one thing which I did not teach you, of course, is basically quadratic forms. Why I did not teach you is I want to teach it when the concept of maxima and minima. Okay, because this form of x transpose ax, this is actually a very useful form, and depending on this x transpose ax, we talk about positive definiteness or negative definiteness of the matrix, semi-positive definite. We talk a lot of stuff. Okay, but again, this if you take the derivative of this, okay, normally this can be done in n vectors. If you take the derivative of this term, normally the answer which I'll just give you as of now is a plus a transpose times x. This is what you'll get. Okay, so a plus a transpose times x, and in case if the matrix is symmetric, that is 2 times ax. We'll use this a lot in optimization, and anyhow, since I'm teaching data science syllabus, doing single variable calculus or single variable optimization, I'll come back here and we will talk things about it. Okay, so this is what we have done in a brief. Okay, now in today's class we'll start single variable calculus. So I'll give you the introduction of what is a limit, of course, in a much understandable sense, and continuity. Okay, normally continuity, people tell limit is equal to functional value. We'll check. Okay, we'll start from the basic and we will slowly march, like how in linear algebra we have started with the definition of a matrix, and then we have gone through. Okay, we have gone through some advanced stuff, some nice interesting thing. Okay, but now if you see this calculus, it will in today's class I'll try to give some idea of limits and continuity, then differentiation of a function, and also I'll try to give some standard graphs, okay, which people can ask you in some interviews hopefully, and also technique for writing or for drawing any graph in general. Okay, sir, how many marks will come from this chapter for civil engineering? In general, for any branch of engineering, normally on an average 4 marks comes from this calculus. Okay, not only single plus multivariable calculus, but I'm not including differential equations and all. If you include total, you'll have 8 to 9 marks. Okay, like total calculus module, but this is only single variable calculus. Now let's start with our first concept, limits and continuity. Okay, now before I ask this concept of limit and continuity, I'll go back to that example which we have understood. Okay, so let a is equal to b. This is one common example we'll use. So this implies ab equal to b square. So ab minus a, or a square minus ab, is equal to a square minus b square. So ultimately if you take a common, you have a minus b, and this is a minus b times a plus b actually here. Okay, so then I have already told you, if you are following regularly, you can answer this. So a is equal to a plus b. Now since b is same as a, we can replace this is equal to 2a. So a is cancelled and 1 is equal to 2. Okay, this is what I have shown you actually, but clearly this 1 is not equal to 2. Ultimately this is wrong, of course. Okay, this is not valid, and obviously the two integers are different. Now mathematically, if people don't understand something, everything looks very perfect here, because I have factorized a square minus b square, which is 2. I have cancelled the common factor on both sides, which is also 2, of course, and I have substituted b as a, which is also 2. So mathematically people don't find any mistake in general many times. Okay, many times people think what's the mistake in this, but the main mistake lies here, where in this step you can see here I cancelled 2 zeros. Since a minus b is equal to 0, it cannot be cancelled. It can't be cancelled. Okay, means basically you cannot cancel 2 zeros. Okay, that's what idea, because if I can cancel 2 zeros, then ultimately I can write 0 equal to 0, then 3 into 0 is equal to 4 into 0 maybe, and I'll cancel zeros and I'll say 3 equal to 4. That's also could be a possibility. In fact, I can show any two different numbers can be equated. Okay, but the idea here is 2 exact zeros, or basically if you have an exact 0, then you cannot cancel that. But in limits we frequently keep cancelling the terms like this. Okay, like we'll write limit x tends to 2. You might have seen this, limit x tends to 2, x square minus 4 by x minus 2, let's say. Then here people generally what we do is we'll write this as x plus 2, which is equal to 4, of course. Okay, this is what you might have seen, of course. Okay, I'll start from the basics, but just giving some bit of motivation in order to start this concept of limit. Okay, then let's see. Now you came to one very important conclusion, that if there are two zeros exactly on both sides, it cannot be cancelled. But at the same time, you are cancelling this x minus 2 and x minus 2 here. Ultimately, you're getting x plus 2 because you're factorizing this and cancelling x minus 2, of course. Okay. Now you clearly know mathematically you cannot cancel two zeros, but you are cancelling this x minus 2 means it tells you something, that x minus 2 is not equal to 0. Correct? So this tells you x is not equal to 2, of course. Okay, because you have cancelled it. So if it is case of non-linearity where 1 equal to 2, no, it's not about the degree, it's about the absolute values. Okay, we are talking. Now let's see, if x is not equal to 2, of course, then again here you can understand roughly we are keeping x equal to 2 and writing 4. Okay, at one particular point in this complete calculation, in these 3 steps starting from here to here, at one point we told that x is not equal to 2 and we have cancelled x minus 2, telling that x minus 2 is not 0 basically. But at the next step we have kept x equal to 2 and we got 4. Okay, so how we can take at one part of the problem x is not equal to 2, but at the same within the same problem at some other step how we can take x equal to 2? This is the question. Okay, so if you ask yourself how or why you are actually putting 2, or if x is not equal to 2, then one question that comes is, what is x? This is what you will get. Correct? Yes or no? Is this clear to all of you? So one thing you can understand, you clearly know when you write this, x is not equal to 2. That's fine. Okay. If x is not equal to 2, then what is the value of x? That's what. Correct? That's the question that obviously comes next. Yes? Yes or no? Correct? So all of you, please type in the chat box. Akhil, Ajay, of course, there are a lot of names. I cannot read all, but anyone, please, all of you, please, confirm. Can you all understand this? Okay. One question that comes in our mind is, x is not equal to 2, of course, 2. Then if x is not exactly 2, then what is the value of x? That's the question that comes up. Okay. Now to understand this concept of what is the value of x, okay, so to answer this question, we move to one particular concept which is called neighborhood of a. Neighborhood of a. Okay. So what's this neighborhood of a? That's the meaning, like the same definition of your neighbors. Okay, so let's say, for example, I generally use this classic example always. So let's say there's a road like this. Okay, I'm just telling this. So let's say there's a road, and let's say your house is somewhere here. Okay, so I'm telling this is like your road and your house is somewhere here. Then definitely the people who are just beside you, let's say if you plot them as this, what are they called? Let's say this is you and these people are standing beside you. Okay, or basically this is your house and people beside you. What are they called? Come on, please type in the chat box. What are they called? They're just beside you. Neighbors, right? Obviously they call your neighbors. So similarly, someone who is here is also your neighbor. But someone who is really far away, he may not be your neighbor. Okay, we'll put some restriction. Okay, let's say for example your marriage got set. Okay, obviously then you'll keep distributing cards and you'll keep inviting people, but then you will keep a limit depending on maybe your budget constraint or depending on the relationship you have with them. Okay, the kind of touch we have with them, you will just keep only a limit. Okay, so similarly, if this is my x-axis, okay, I'm talking about single variable calculus, this is my minus x. Now let's say this is a real number a, for example. Okay, so this is a real number, x is equal to a. Then a plus 1, and between any two integers there are infinitely many real numbers. So in between any two real numbers also there is infinitely many real numbers. Like let's say if I ask you what are the number of real numbers between 2.111 and 2.1112, for example, you can write infinite number of real numbers between these two, correct? Because I can keep changing the 5th decimal, I can keep changing the 6th decimal, I can keep changing the 7th decimal, like I can write infinite number of numbers. But the main story here is, out of these infinite numbers, what happens? Few numbers lie very close to this a. Okay, if a is here, maybe a plus 1 is somewhere far away, a minus 1 is also somewhere far away. Okay, maybe somewhere far away. Now there exists some limit or some set of real numbers which lie very close to a actually here. Okay, then if this value, if I call this distance as delta, delta is a small number. Okay, delta is very small number, of course. If that number is delta, then ultimately this value of x is nothing but a minus delta, correct? And the value to the right side, if this also I call it as delta, the same value, then this is called a plus delta. Okay, now if I keep the limits as a minus delta and a plus delta, you can understand every value which falls within this interval a minus delta to a plus delta will lie very close to a, and that set contains all the real numbers which are very close to a. That's called neighborhood of this a actually here. Clear? Now let's see neighborhood of a for any real number x is equal to a. The values of x where x belongs to a minus delta comma a plus delta, where delta is positive but very small, is called neighborhood of a, is called neighborhood of a, of course. Okay, because ultimately if delta is very small, then the values which are within this interval a minus delta to a plus delta, these fellows lie very close to a, and that's called a minus delta to a plus delta, and all the values which fall in this is called neighborhood. Now ultimately people which are to the left side of this a are called left neighbors or left neighborhood, and people who are to the right side of this a is called the right neighborhood. Okay, so which means you can say x belongs to a minus delta comma a, this is called left neighborhood. Why I am teaching all these definitions, please be attentive. Left neighborhood of a. Okay, so this is called left neighborhood of a, and x belongs to a comma a plus delta, this is called right neighborhood of a. Right neighborhood of a actually. Okay, now if you merge these two things, if you merge your right neighbors and left neighbors, you will get something called deleted neighborhood, which is a very important thing actually. So you'll see deleted neighborhood, which means you don't include yourself in the neighbors, you have deleted yourself. So x belongs to a minus delta comma a plus delta minus, we are subtracting one element from this set which is you yourself. Okay, so this is called deleted neighborhood, and this is the left neighborhood, and this is in the right neighborhood, of course. Okay, so if you take any real number, then the closed set of real numbers which are to the left side, which are less than that particular real number, is said to be the left neighborhood and the right neighborhood. And many times this is denoted with a minus, and this is denoted with a plus, of course. Okay, so a minus tells you that x lies in a minus delta to a plus means slightly a value more than a tells you that the value lies within this interval. Okay, and please make sure, because many times I see students commit mistake, this a minus is something different from minus a. Okay, if a is here, minus a could be maybe somewhere there. Okay, but a minus is basically this part. Clear to all of you? Yes or no? Can you all understand the difference between this a minus and minus a? Minus a could be somewhere far away, which is not at all in the neighborhood, but a minus is that set of real numbers which are slightly less than a but very close to a. Okay, clear to all of you? Did you all understand the concept of neighborhood? First, is there anything doubt that I have written on this board right now? Every one of you, everyone, please type in the chat box. Anything clear to all of you? Yes, each and everything. Okay, now if this is clear, now we'll come to the concept of limit. Okay, we'll see what is a limit, of course. Now, limit of a function. Limit of a function. Limit of a function. Now I'll write, no doubt, correct? Okay, now I'll write two statements. I'll give you two definitions of limit, of course. First one looks little messy, but don't worry, I'll explain term by term. Second, you'll easily understand, okay, by yourself. So let's see. A value L is said to be limit of a function f of x if for all x minus a mod x minus a less than delta, there exists a value, a small value but positive, a small positive value epsilon such that mod f of x minus epsilon, mod f of x minus L is less than epsilon. Okay, mod f of x minus L is less than epsilon. It is denoted as, it is mathematically denoted as, it is mathematically denoted as limit x tends to a, f of x is equal to L. Okay, this is what you'll get. Okay, so basically this is defined in such a way that limit x tends to a, f of x is equal to L. This is one definition. Or a value L is said to be, a value L is said to be limit of a function f of x, a function f of x if f of x tends to L as x tends to a. Okay, this symbol, this bracket should be read as, it should be read as tends to. Okay, you should read that as tends to. Okay, which means approaches, means approaches. Okay, so it is, which means it approaches actually here. Clear? So it means approaches. Now let's see what these definitions actually tell you. Okay, so this definition is of course very much easy to understand, but this is the perfect mathematical definition. Look, I'll draw a graph and we'll explain it. This is, let's say, 0, and this is x, and this is your y-axis, and of course this is y is nothing but your function f of x, whatever you're taking. Okay, now let's see, if I take a function something like this. Okay, so let's say there's a function. You can clearly see intentionally I have broke this function. Okay, means basically this function is not smooth continuous. I have made a breaking in this function. Okay, so let's say for example you have tan x. Okay, then at x equal to pi by 2, tan pi by 2 is infinity, and you cannot practically plot it. So we'll see this function has got a break. Okay, and try to understand something here. This is your x is equal to a, of course. Okay, so that's your x equal to a. Now try to understand one thing, mod x minus a less than delta. Okay, so let's say again there is some value which is L, of course. Okay, so I'm making it L. Okay, and guys, I'm repeating, I mean basically you can see I'm telling you one thing, this L do not have any connection with this f of x. Okay, so this is the function y equal to f of x. Of course we have plotted some function, depending on f of x you'll generate the shape, but let's see, this value is L. This L is just a number or some real number on y-axis, that's it. Okay, this L do not have any connection with this f of x. Clear? Now let's see what I mean. Mod x minus a less than delta, which means mod x minus a less than delta. If you have studied inequalities, I'll just tell you one thing, mod x minus a less than delta, this actually tells you minus delta less than x minus a less than delta, of course. Okay, so this tells you a minus delta less than x less than a plus delta, of course. Okay, so this ultimately tells you x belongs to a minus delta comma a plus delta, of course. Okay, so this is what it tells you, which means if you choose a sorry, yeah, if you choose a interval such that, observe carefully, this is a bit important stuff. This is a minus delta and this is a plus delta, for example. Okay, now at this point, if you calculate f of x, okay, so let's say at this point, if you calculate f of x, how do you get f of x? At this value, if you go to this function and if you just cut this on y-axis, you'll get the function value at this value of x, correct? That's what the graph is, of course. Okay, it is plotted on x versus f of x. So you take any x, you just go up and strike the graph, and from that, if you take a horizontal and if you look at the point of intersection with y-axis, that's the functional value. Now again, similarly here also you can understand one thing, this has actually cut it here, but you can understand one thing, if I start approaching towards a, okay, so let's say I am initially here, but let's say I moved somewhere here. Now from here to here, when I move, you observe one thing, this actually, if you look at the functional value came here. Similarly, if you just move further, you can understand, this, it has come here. You can understand one thing, as this x, initially my x is here, now as this x is moving towards this a, this function f of x is initially here. Now as my x is moving towards a, if I start at this point and if I keep moving towards a, my f of x starts keeping towards L. Yes or no? Correct? Can you all understand this? As x is moving towards a, this f of x is marching towards L. Correct? Can you understand this? Yes or no? Please type in the chat box. I've started somewhere in the neighborhood and I'm going very closely towards a. As I move very closely towards a, my f of x goes very closely to this L actually. Okay. Now one more point. Here I just told you x approaches a. Okay. I've told you x is initially in the neighborhood of a and x is approaching a. Now when I tell you x is in the neighborhood of a, x can be to the left of a or x can be to the right side of a. Correct? Remember, I'm telling, if x is in the neighborhood of a, of course, x can be in the left side or neighborhood or x can be in the right side neighborhood. Now when I'm telling x approaches a, if x is in the left neighborhood, it approaches in this direction. If x is in the right side neighborhood, it approaches towards the left side direction. Correct? It approaches towards left actually. Means when we define this concept of limit, we are not putting any restriction on the side on which x is lying actually. Okay, we are just telling x is in the neighborhood and it's approaching a. X can be in the right neighborhood and approach towards left, or x can be in the left neighborhood and can approach towards right. Okay, so that's why the concept of left hand limit and right hand limit comes up, because we are not specifying the direction when we are defining the limit. Clear to all of you? Now let's see here also, if you look at this point, initially when you have here the functional value is here. Now when you start moving, okay, so let's say from here you came here, then when you slightly march, then ultimately the functional value is this. Okay, similarly if you come much close towards a, you will observe this guy moves again towards L. Okay, so that's why this L is said to be the limit of this function, because at this point x equal to a, see, limit, continuity, differentiability all are defined at a particular point. So at this point, if x is in the neighborhood and it's approaching towards a, this function will keep approaching towards L, and this L has nothing to do with this function. Clear? Okay, in fact at this point exactly at a, the function has, it doesn't have any value, it got broken. Okay, intentionally I have done this because to show you there is no functional value here. Okay, so this is what you have. Now clearly this definition also holds as long as you keep this difference between x and a. X minus a is some small value, f of x minus L is also some small value, because let's say when you are here at this point, and if this is the difference, then ultimately correspondingly some epsilon difference is also there between f of x and L always. That's the upper definition. That's it. Okay, the upper definition tells you that if there is a difference between these two, then definitely there is a difference between these two also. F of x and L also has difference, because ultimately you can see this L and f of x is not there here. Okay, is this concept of limit clear to all of you? Yes or no? Limit is that real number to which the function approaches as x approaches to a particular value. Clear? that value L is declared as the limit of the function. Okay, is this clear or not? Now why we are interested in limits? Okay, that's the main important thing. Suddenly when you're doing physical experiments, there is a sudden jump that you see. Okay, can you please tell again the first definition? Yeah, definitely. See, what I have told you is this x minus a is less than delta, which means x is in the neighborhood. Whenever x is in the neighborhood of a, then ultimately L will be in the neighborhood of that f of x values. That's what. F of x will be in the neighborhood of L. That's what. Okay. So if x is in the neighborhood of a, then this function value will be in the neighborhood of L. That's what. Okay, you can see from graph. Now, so this is the concept of limit. Now I'll just work out one example and we'll show you how we actually calculate the limits in general. Okay. So if I ask you one thing, if I say limit, don't worry, I'll talk about mod x function in detail, but I just want to give you. Let's say limit x tends to 1 or x tends to 0 mod x. If I ask you to calculate this, what is the answer? Can anyone tell me? What is the answer? Can any one of you tell me? What is the answer? Can any one of you tell me? Limit x tends to 0 mod x means if x is coming towards 0, what is the value of mod x? That's the question. 0, correct? Yeah, this is 0, of course. This is 0. 0. Okay, that's 0, of course. Okay, now let's see how that is 0. I'll show you. Of course, many of you know if you put this 0 here, you'll get 0. That's how you're intended to say 0. Now let's see if you want to calculate a limit. Okay, a value L is said to be limit of f of x at x equal to a if limit x tends to a plus f of x is equal to limit x tends to a minus f of x, because it doesn't matter from which side you approach, your function value should give the same L. Okay, and this is called right hand limit. Right hand limit. Right hand limit. The meaning of this x tends to a plus is x is initially in the positive or basically in the right neighborhood of a and it's approaching towards a, and like limit x tends to a minus is nothing but the left hand limit. Left hand limit, and these two limits should be equal. Okay, if you want to define a limit at any point, then ultimately this left hand limit and right hand limit should definitely match each other. Okay, only then the definition of limit is valid, because in the definition of limit we did not specify the direction. So if we didn't specify the direction, whatever the direction you take, either from left side or right side, if the value is approaching to a either from the left or from the right, the function value should actually go to the same L, of course. Okay, that's what. The limits are always same? No, they're not always same. I'll give you examples. Okay, so let's see. Limit x tends to 0 mod x. If you want to know, for example, how this is 0. So first of all, we know mod x. F of x is equal to mod x. If you want to see this, this mod x is nothing like x for all x greater than or equal to 0 minus x if x is negative. Okay, because you can see if x is negative, then minus x is positive ultimately, and mod x function always gives you positive. So x tends to a minus means it comes from left side. Yes, of course. Okay, x tends to a minus is x is initially in the left neighborhood, so it moves towards right and approaches a. Clear? Now this is the expression for mod x, of course. Okay, if x is positive, then mod x, let's say for example if I ask you mod 5, you will directly say it is 5. Whatever is here, that is here if x is positive. If x is negative, if I ask you mod of minus 5, minus of minus 5 gives you plus 5. Okay, so that's how we have a function like this. Now what limit value tell us? The value to which the function is approaching. Just give me 1 minute, I'll explain. I'll take physical examples. Now let's see here. If you calculate left hand limit, for example LHL. Okay, so if you calculate this left hand limit, then try to get one thing. Limit x tends to 0 minus mod x. This is what we have. Okay, If you write limit x tends to 0 minus mod x, that means x is less than 0 because it's in the negative or basically in the left neighborhood and it's approaching towards 0. This limit can be written as limit, okay, basically you can use LT or LIM. It's okay. So LIM x tends to 0. Now we will remove this minus sign depending on the way how we modify this function. Okay, like if x is tending to 0 minus, then you know x is less than 0. If x is less than 0, then mod x value is equal to minus x, correct? If x is less than 0, mod x should be minus x. So by removing this negative sign, I can keep this x, of course. Okay, sorry, minus x is what I can keep. Now when you keep x equal to 0, this value is 0. Similarly, if you calculate right hand limit RHL, then this gives you limit x tends to 0 plus mod x. This tells you limit x tends to 0. Then when x is in 0 plus, that means x is slightly more than 0, so x is positive, so mod x is x, that's it. So when you keep 0 here, this gives you 0. Now both these are giving zeros, so that's why, therefore, since limit x tends to 0 minus, I've started with a simple example, of course, mod x is equal to limit x tends to 0 plus mod x is equal to 0. This implies, since both the limits are equal, we can just write it simply, x tends to 0, mod x is equal to 0, that's it. Okay, so this is how we can write the function of, or basically the limit. Okay, now you can ask me why I'm keeping 0 here. Now basically in this case, this definition tells you as this x is moving towards a, this f of x is moving towards this number. That's what it tells you, and you can put equality sign only if you write this LIM. If you are not writing LIM limit, then ultimately you cannot put this equality sign because f of x and L are not equal. That's what I have told here. Okay, so mathematical representation of a limit is basically from this definition. You cannot write f of x equal to L if you don't put this limit. Okay, because they are not equal. Clearly it is, there is some small difference between them. Okay, so limit x tends to a is what you should keep if you want to represent. So can you please tell this with graphical method? I'll tell you. Okay, just because I didn't give you graph of mod x, I'll give you maybe in the next 30 minutes I'll give you some important graphs. Okay, then we'll teach. And coming to meet Rathod. So what limit value tell us? Limit value tells us to what value a particular function approaches with time. Let's say for example, if you are dealing with some signal, okay, then practically there could be some jump in the signal suddenly. Okay, then when there is some jump in the signal mathematically, but physically, you know, the system takes, even though the time is very short, the system takes some time for physically having the jump. Okay, so what we'll do, exactly at the points where the functions fail, we'll calculate the left limit and right limit, and we will decide one particular value at that point where it's failing. Okay, like I'll show you one example. Okay, so see here, this is how you'll calculate the limit, of course. Okay, now if you just see some important things, if okay, this point we'll teach later because I want to teach you differentiation also. So the definition of limit is this, basically the value to which the function approaches as x approaches to a particular value. Okay, that's what, and these are the two definitions. I hope everything is clear to all of you now. Okay, did you understand how depending on the right neighborhood or left neighborhood we are modifying the functions here? Okay, of course this is mod x function. Similarly, if you have other functions depending on left neighborhoods or right neighborhoods, you'll modify the functions. Okay, we'll see, we'll have a lot of examples, we'll see. Okay, clear to all of you? Yes, is this understandable to each and everyone? Please type in the chat box. Every one of you should type in the chat box quickly, make it fast because I just want to confirm the things. Okay, then let's observe continuity of a function. Okay, continuity is very much important again. So continuity of a function. Continuity of a function. Now many times you might have seen these functions where f, okay, so it's clear, yeah, good. So many times you might have seen functions like this, f of x is equal to 1 by x minus 2 at x not equal to 2, and maybe 4 at x equal to 2. Okay, so you might have seen functions like this. These are called split functions. Means basically you define some general form for a function, but at few points this functional form is not finite or basically not valid. So at the points where it's not valid, or basically the division with 0 is not defined, we will define a value as functional value like this. Okay, physically how we are getting this 4 and all, that's a different story. It depends on the experiments and all, but let's say you have one function of this sort. Okay, then this is called a split function clearly. Now you can understand one thing: whenever the function is split or functional value is not defined at a particular point and it's defined in a different way, but how to check whether the function is continuous or not? Okay, so that's what we'll check it up. So let's see how we'll check it. See carefully. Many of you might have studied this definition. A function f of x is said to be continuous at a point x equal to a, x is equal to a, if limit x tends to a, f of x is exactly equal to f of a. Okay, this is the condition for continuity. Clear? So this is the condition for continuity. The functional value at that point should be exactly equal to the limit value. Okay, so let's check again. I'll explain you graphically. So let's say you have these two functions. Okay, so you have these two functions. This is origin, this is x, and this is y. Okay, now again I am forming the same function in order to explain things. So this is the function y is equal to f of x, and you have this x is equal to a, of course. Okay, so this is x is equal to a, that's what you have. So if this is x is equal to a, exactly at this point the function is not very smooth. So let's say this is the value which is defined, like you see 1 by x minus 2, maybe this function. Now when it is 2, it is defined 4 is the value. Okay, so like that, exactly at the point where this function is breaking, we define the function by using some other value. Okay, now let's see clearly by the same story whatever we have done. This is L. Okay, L is just a real number, and clearly so piecewise function or discontinuous. Is piecewise function a discontinuous function? It depends. Okay, that's what I'm telling. Every piecewise function need not be discontinuous. We'll see. Okay, so let's see here. If L is equal to L is actually the limit. Okay, so say L is limit. L is of course limit x tends to a, f of x, for example. Okay, so the same story what I have told you. If you start somewhere here, then this is the functional value. So if you start, and this is a minus delta maybe, so if you start marching, then ultimately this function, as you move towards a, this function keeps moves towards L. Similarly, if this is a plus delta, then this is the functional value. Okay, now if you keep moving towards a, then ultimately this functional value keeps moving towards L, of course. Okay, so as this moves towards a, this f of x also moves towards L. Now tell me one important thing. Clearly you can observe one thing: this function is not continuous. You can see physically there's a break in the function. Okay, it's piecewise and there's a breaking in the function. It's not a smooth curve. Okay, if you leave some ball here, it won't reach this point, it will drop somewhere. Okay, it's discontinuous. Now if you want to make this function continuous, for example, if you want to make this smooth, the only thing that should be possible is the functional value at this point is defined at here. Okay, maybe this is f of a. Let's say if I call this f of a, okay, because I have defined my function like this, f of a, of course. Okay, this is what I have defined. Now if this graph has to become smooth, ultimately this point which is here should come here, yes or no? If this point which is here initially, if this point comes here and stays in between, then ultimately this becomes a continuous function at this point. Yes, will you all agree? At this point, if this function has to become continuous, this point should come and settle here, then this function becomes smooth at this location. Yes or no? Come on, quickly type in the chat box. Correct? If this point comes and settle here, then ultimately at this point x equal to a, this function becomes smooth in this region. Okay, what is the physical meaning of this point coming and settling here? this f of a is getting equal to L. Yes, correct? Yes or no? Because if this is by L, then the point physically come from here. If it's coming here, that means this f of a is coming and exactly settling on L will make this point come and settle here. Okay. Now, if this point has actually come and settle here, then if this becomes smooth, continuous at this point, for continuity, for the function to be continuous, for the function to be continuous at x is equal to a, ultimately your f of a should be equal to L, and that's equal to limit x tends to a f of x, because L is nothing but the limit. Therefore, at a point, if the function has to be continuous, the limit value of the function and the actual value of the function both should be same. That's how we get this condition. Okay, you might have seen this in many books, of course, even in your class 11, many times you might have seen, but physically why it happens is, okay, clear to all of you? Yes or no? Please type in the chat box. Yeah. Okay, now let's move forward. We'll try to understand what is differentiation of a function. Okay, see, again, I'm not, limits is not finished. Okay, so above function is told is not continuous, right? Yeah, previously whatever I have told without this dot is not continuous. Okay, after being this point here only it becomes continuous. Okay, now please don't think the concept of limits is done. I'll give you a lot of formulas, lot of important things in so can you please give some real life examples? Why not you take, let's say you have this equation, okay, projectile, and let's say you plot a point here. Okay, then if this is projectile, then ultimately this equation, if you plot, you'll get y equal to, if you project the body with a velocity u, okay, and this angle is theta, for example, then the equation of this parabola is tan theta x minus g by 2 u square just a minute, I'll write it straight maybe, okay, because space won't be minus g by 2 into mod u whole square cos square theta into x square. Okay, now if I ask you the question, exactly at theta equal to 90, if I throw, what would be the equation if I ask you this? Okay, then ultimately, you know, exactly at theta equal to 90, if you put exactly theta equal to 90 here, in this case, this shows some value infinity, and this 1 by 0 also exactly gives you infinity. Means this equation is completely valid if this theta is not equal to 90. Okay, if theta is equal to 90, exactly at 90, this function will not be valuable. Okay, because if you put theta equal to 90, things comes up in terms of infinity. But if you do this analysis at theta equal to 89.9, for example, okay, then ultimately you'll still get parabola. Like you can calculate by limit theta tends to pi by 2. If you calculate this equation, tends to pi by 2, tan theta times x minus g by 2 u square cos square theta times x square, because here theta is not exactly pi by 2, it is only approaching pi by 2. So when you encounter points where the functional value exactly at that point is not defined, you will generally calculate the functional value in the very close interval. Let's say at theta equal to pi by 2, I cannot calculate what is the exact path, okay, or basically this equation is not valid. Then ultimately I'll try to calculate at theta equal to very close to 90, so that then I'll observe what's going to happen at theta equal to 90. So likewise, when there exist points where you cannot exactly study the data there, you will slightly move in the neighborhoods and you will study the data, so that physically systems do need some time for change or time for any change in the characteristic behavior. Then ultimately within that small time, that there cannot be sudden jump. Okay, so there is some continuity that exists in between that small jump, so we can get the value at the point where there is discontinuity. Okay, so that's what we can actually do. Shiva Krishna, with those 8 classes of linear algebra, can I get concepts of machine learning? No. Okay, because machine learning algorithms are completely different. Like you have regressions, okay, in which we'll deal again in probability. Okay, so you can have supervised machine learning or unsupervised learning. Okay, you have a lot of things. Okay, then 𝐂𝐚𝐴, we have a lot of other things. So that's not the complete stuff, but whatever I taught you, that definitely is useful as a mathematical background for linear algebra. Okay, for machine learning. Clear? Okay. Because I didn't teach machine learning algorithms, to be frank. Okay, I've just taught you the basic mathematical need that you require for learning ML algorithms. Okay, especially when you go for supervised learning or unsupervised learning or the nearest neighbors, 𝐂𝐚𝐴. Okay, in all these spaces you'll find the advantage of knowing these things. Okay. So chalo. Anyway, let's get back to the story. So basically what I want to tell you is I'll again come back limits in tomorrow's class, because to calculate majority of the limits, we'll apply something called L'Hospital's rule, where you will be in need of derivatives. Okay, so today we'll define what is a differentiation of a function, and I'll give you some standard derivatives, and using those we'll again come back to limits, and we will calculate a lot of limits. Okay, so we'll come back to limits again in tomorrow's class. Now let us check what is differentiability of a function. Okay, differentiation of functions, or basically how to check differentiability of a function. Okay. So please suggest me some best books for linear algebra. I have told you know in last class. If you just a minute, because one of our friend is interested in knowing books. So if you just want to learn linear algebra, then ultimately this linear algebra by Gilbert Strang, this is fantastic book for learning linear algebra. Again, I'm talking in terms of in-depth linear algebra, not for the GATE syllabus. Okay, and for machine learning, you can go for this book called Probabilistic ML, Machine Learning. You can visit Kevin Murphy. Kevin P. Murphy. This is a very good book, of course. Murphy. These are the two fantastic books. You can, one gives a solid background about, you know, very good background about your mathematical needs that you need, and ultimately Probabilistic Machine Learning by Kevin P. Murphy is a fantastic book again. Okay. CH, what is CH? It's okay. Alex, CH is pending. What is CH? 𝐂𝐤𝐴. Okay, got it. Yeah, fine. We'll finish this at the end. I'll come back. Okay, because this discussion will again get cut. Okay. 𝐂𝐤𝐴 name is very simple, of course. We'll deal maybe in the last 10 minutes of the class. Okay. Fine. So let's see differentiation of a function. So what is a differentiation of a function? Of course, or basically when we deal the derivatives. Okay. So derivative, the derivative of a continuous function f of x at a point x equal to a is defined as limit x tends to a f of x minus f of a divided by x minus a. It is denoted as dy or df of x by dx at x equal to a, or in simple terms it's denoted as f dash of a, of course. Okay, then let's see, if you write this, f dash of a is nothing but limit x tends to a f of x minus f of a divided by x minus a again. In generalized form, the derivative of a function at any point in general the derivative of a function f of x is given by y equal to f of x. Let's say y is equal to f of x, some function y equal to f of x is given by dy by dx or f dash of x is equal to limit h tends to 0 f of x plus h minus f of x divided by h, of course. Okay, so this divided by h. Actually both these formulas are analogous, I'll show you. Okay, and this is called first principle of differentiation. This is called first principle of differentiation, and using this you can calculate the differentiation or derivatives of any function which is differentiable, of course. Okay, so if this limit exists, we'll say that the derivative of the function exists, or basically the function is differentiable. If this limit does not exist, because obviously it's a limit, again derivative is given by one more limit. So if this limit exists, okay, right neighborhood, left neighborhood, whatever, if this limit exists, then the function has a derivative. If this limit do not exist, then the function do not have a derivative, of course. Okay, we'll check it up how these formulas actually came. I hope many of you might have seen this, correct? I hope many of you might have seen this, correct? First principle of differentiation. F dash of x is equal to limit h tends to 0 f of x plus h minus f of x divided by h. That's what you write, correct? I hope many of you might have seen this. So, yes? Now, do anyone know how this comes up? Do anyone of you know how this function, or basically how this? So here a can be from any side. A is some number. A is some number, but coming is basically tending. Okay, hi Krishnan. A is any real number, and x tends to a means x is somewhere in the neighborhoods and it's approaching towards a. That's what. Clear? Now let's see how these things come. First of all, if I again draw a function, what does a derivative physically tell you? That's the main important understanding one should get. This is a 0 x y, okay, and y is equal to f of x. If you draw any function, I told you it should be continuous. Of course, you'll come to know why it should be continuous also. So let's say this is some function y equal to f of x. Some function y is equal to f of x. Maybe if this is sin x, then we'll have a different shape. If it's tan x, then we'll have some different shape, whatever. Then y is equal to f of x. Now try to understand something. Let's say at this point I want to calculate the derivative. Okay, x. So this is ultimately f of x. Okay, ultimately f of x. Then maybe this is not very, but I hope you can get. Yeah. So at a particular value of x, you have some function value f of x. That's how. If this is x, then correspondingly that's f of x. What does derivative tell you? If you are writing dy by dx, okay, dy by dx, rather than that, we'll go for delta y by delta x. This is what the term which is very much of interest, okay, because when y is depending on x, okay, so let's say for example, if I'm doing time period of a simple pendulum experiment, for example, okay, then ultimately if I take the same length of a pendulum and if I swing it on earth, it gives you some different time period. If I swing it on moon, it gives you some different time period, because you clearly know there is a variation of g, and on gravitation, attraction due to gravity, or basically acceleration due to gravity is 1/6 only on moon. Okay, so ultimately pendulum comes up a bit faster. Okay, so t will be high. So pendulum, if t is high, then yeah, pendulum comes slow, of course. Okay, then practically whenever you try to derive physical relationships, ultimately one variable keeps depending on other variables. Okay, right now we are dealing single variable calculus, so let's say the unknown is depending only on one variable. Okay, so we are interested in identifying, if you change that independent variable by some small amount, what is the corresponding change is coming in y. That's what we are interested in. Okay, so when this y is depending on x, now if you slightly disturb x, what is the change in y? This is the important question. Okay, because ultimately we should know that's the change. Calculus is basically called the science of variation. So if something is varying, then with respect to this something, how the other quantity is changing, that's the important. Now delta y by delta x, here if you take other value, let's say x plus h, okay, I am defining one more point. So my x is actually initially here, now it has moved somewhere here, x plus h. Now if this is x plus h, then correspondingly this is my f of x plus h. correct? Yes or no? Because if my x moves here, my f of x has also jumped to some extent. Clear? So can I ask something? Yeah, why not? So delta x can be positive or negative, right? Yeah, it can be anything. The main thing is you have to disturb it. That's it. Okay. So it is at some particular value. We are just disturbing it. You can even disturb towards left. Doesn't matter. Okay. Now let's see. If you take delta y by delta x, the initial change in delta x you have produced is nothing but the initial change in delta x that you have produced is nothing but x plus h minus x. This is the change in x what you have given. Okay, means basically this value is nothing but, if you have length, if you want to calculate this length, this coordinate minus this coordinate, x plus h minus x gives you x. Now for this change in x, what is the corresponding change in y actually? Okay, so you see you have changed x, of course. Now when you changed x, y got changed by this much. So what is the change in y? F of x plus h minus f of x. This is what you have. Okay, now ultimately if you simplify this, x and x gets cancelled, so you have delta y by delta x is equal to f of x plus h minus f of x divided by h, of course. But you want to check differentiability at a point. Okay, so because ultimately continuity, differentiability, all these points are defined at a particular point. Now if this region has to be a point, this x plus h should lie very close to this x. Yes or no? Correct? So for a very small change in x, let's say you want instantaneous, for a very small change in x, ultimately x plus h should move towards x. Okay, means basically x plus h and x should be very close. They should be very close to each other. That means h should tend to 0. That's what. So therefore if this difference is very small, instead of taking delta is the change, okay, d is the difference. That's the notation we have. Basically people who have developed calculus followed. Delta gives you change, d gives you the small difference. Okay, so therefore the value of delta y by delta x, if delta x is very small, this is given as the small difference in x, which is dx, then a small difference in corresponding difference in y is dy. This is nothing but limit delta x tends to 0, which means h should be very small. This function f of x plus h minus f of x divided by h. That's how we get the definition. dy by dx means zooming into the function, or is it like studying how perturbing a quantity affects the other? It's like perturbing a independent variable and studying how the dependent variable is changing, but the perturbation is very small. Perturbation means basically disturbance. Okay, so that disturbance is actually very small. That's what we are giving. Clear? If you slightly change this independent variable, then what is the change in the dependent variable? That's what the interested stuff. Clear to all of you? If you have a doubt, please ask. Okay, you need not take permission. You're granted for asking doubts. No issues. Okay, fine. You can ask a number of doubts. Doesn't matter. Is this clear to all of you? Did you understand how did we achieve this first principle of differentiation? Because ultimately that's the fact. If x is changing, what is the change in y? That's why. Okay. Now one important point. This limit is basically putting dh instead of h. Dx instead of dx, it's putting h. That's what. Okay. Now let's see one interesting stuff. What does this limit physically tell you? Okay, like let's say for example, if I ask you, there is a function f of x is equal to sin x. Of course we'll see how these things come up. Then if I ask you f dash of say pi by 3 for example, okay, f dash of pi by 3 is what I asked. Then all of you know, you'll differentiate this function. F dash of x is equal to cos x, because derivative of sin is cos. Then you put x equal to pi by 3, then this is cos pi by 3. You will get one number which is 1 by 2 in this case, of course. Okay, so 0.5. Now what does this 1 by 2 tell you physically? Okay, what does this, why small disturbance, why can't big like stock market crash? Because things are not very smooth actually. Okay, here we are dealing for smooth functions as of now. We are trying to check the differentiability and all, but in general whenever you slightly disturb, we'll study what's the change. Then for the larger perturbations, how this change is going to be amplified, that's a different story. Okay, again you have to transform theory and all for studying, but in defining derivatives and all, when you slightly change, okay, it's when you take the smallest difference, how the function is actually changing. That's the stuff all about the differentiation. Okay, now Clear? Small change in x. Okay, so small change in x is h. H is the amount of change. Okay, that's what we have taken. Clear? Because if this point is defined at a this derivatives and all are defined at a point, of course, because clearly, if you change this point, then ultimately this value changes. Okay, so if you want to define derivative at a point, ultimately this h has to be very small. That's why. Clear? All doubts done? Okay, is this clear to all of you or not? Just a minute. So please type in the chat box, is this clear to all of you? Everyone, quickly type in the chat box. When h is very, very small, ultimately these two become very close, and instead of length, you will achieve a point on the function. Okay, see, if h is large, then ultimately these two go very large and this becomes length. Okay, but when h is very small, these two becomes very close and these 2 points keep converging and there comes almost a point on the function. Okay, clear to all of you? Yeah. Now, so yeah, now the question is, what does this 1 by 2 tells you? That's the idea. Okay, what does this 1 by 2 physically tell you? Well, in fact, if you calculate f dash of x, what does this f dash of x gives you? This function gives you. Okay, so let's see. Geometrical meaning of a derivative. Meaning of a derivative. Geometrical meaning of a derivative. Let's see. For a function f of x, for a differentiable function f of x, for a differentiable function f of x, f dash of a is nothing but slope of tangent to the function at x is equal to a. At x equal to a. Like you can see, in fact, if you have this graph, again, I keep drawing this many times, of course, 0, x and y, and of course your y is actually your f of x. Then let's see, if you have a function, okay, so let's say you have some function, for example. Okay, so you have some function y equal to f of x. Again, this is for some general function y equal to f of x. So let's say if I have this value as x is equal to a, for example, if I have this point x equal to a, and let's say the function is differentiable, means I can physically draw a tangent to that function. Okay, then if I draw a tangent, you can see this tangent comes up something like this. Okay, so this is how we have the tangent. Clear? Now if this is, oh sorry, yeah, if this is the tangent, then since x is your independent variable, we are taking, that's how y is function of x. So if this angle is theta, the slope of this line is nothing but tan theta. Slope is nothing but tan theta, correct? Because ultimately, if this line makes an angle theta with x-axis, the slope of the line is tan theta. You know, it's called tan theta. Do you know, anyone of you? Do you know, like if a line makes an angle theta, then slope is tan theta. Any idea how it comes? Idea? You have an idea or not? Please type in the chat box. If a line is making an angle theta with x-axis, then slope is tan theta. No idea? Okay, fine. See, then why you're staying silent? If you have doubt, please ask. Okay? Yeah, many of you know. Okay, but for people who don't know, we are just giving some hint. You all know this formula. Let's say if this is maybe some school stuff which you can see x and y, let's say you have 2 points. Okay, you have a line segment, for example this line segment, and let's say I'm extending this intentionally such that this line segment would have made an angle theta with x-axis. Okay, fine. So let's say this point is x1 y1 and this point here is x2 y2. Okay, this angle is theta, this angle is theta. Okay, I'm taking in the positive direction because to make the job easy, it could be same in any of the 4 quadrants. Okay, now let's see if I make projections on this. Okay, so see here, ultimately, you know, this point is x1, this point is x2, similarly this point is y1, this point is y2. You all might have studied the slope of the line joining 2 points is nothing but y2 minus y1 by x2 minus x1. You might have studied this formula, correct? y2 minus y1 by x2 minus x1. Now let's observe something here. If this is a straight line, if you join this, okay, you join solidly, okay, maybe can draw a solid line, of course. So if you draw a solid line like this, and of course this is also a solid, clearly you can understand these two are parallel lines. So if this is theta, this is also theta. Okay, this is also theta, clear? And this is y1, this is y2, so this difference is y2 minus y1. So this gives you y2 minus y1, and this is x2 minus x1. So if you take tan theta, y2 minus y1 by x2 minus x1, which is this. Okay, so this is also same as tan theta. So if a line makes an angle theta with x-axis, then ultimately the slope value is actually tan of that angle. Okay, which you can see basically from this simple idea. Okay, here since it's a straight line, it doesn't matter you take very small change or very large change because the slope is constant throughout. Okay, that's why. Now coming here, the slope of tangent at x equal to a. Now ultimately, like for example here, instead of x equal to pi by 3, if I have given you x equal to pi by 6, then the value would be different, because if I draw a tangent at this point, the tangent will have some different slope. Okay, the angle made by the tangent would be something different and slope would be something different. So this, at different points the orientation of the tangents keep changing, and ultimately the corresponding functional value keeps changing, of course. Okay, that's what you get. So slope of tangent at to the function at x is equal to a. Now my question here is okay, so this is what we can say, f dash of a is equal to tan of angle made by the tangent with x-axis. Okay, this is one important understanding from the concept of differentiation, which is derivatives. Now I just want to ask you one question. First of all, if a function has to have a limit at a point, is it mandatory the function has to be continuous? Type in the chat box. If a function has to have a limit, is it mandatory that the function has to be continuous? Like we have done a, like for example when we are defining limits, oh sorry, something white I have done left. Okay, so when we are defining limits, I've told you if this limit L has to exist at this point, is the function has to be continuous? Is it mandatory the function has to be continuous? Is it mandatory the function has to be continuous? Need not, correct? So if limit has to exist, function need not be continuous, because you can see this L is existing even though the function is not continuous. Here you can see there is a break. Clear? Need not be, correct? The function need not be continuous. Okay, for the limit to exist, the function need not be continuous, which you can see here. Okay, but if you want your function to be continuous, definitely its limit should exist. Okay, then only you can define continuity, because continuity is defined by this condition. If this condition has to be valid, first of all this limit has to exist. So that's why this limit L has to exist if the function has to be continuous. Okay, and if the function has to be differentiable, then ultimately the function has to be continuous. I've told it's continuous because now after reaching this point, let's say if this point is not there, okay, means let's say there is some small patch here. Okay, I'll explain here why function should be continuous for differentiable. y function has to be continuous, y function has to be continuous for being differentiable, for being differentiable, for being differentiable. See, if you want to know whether the function is differentiable or not, ultimately at that point you will take a tangent, okay? And if there is a sharp edge, then how do you define tangent? Basically, you take in the right neighborhood and left neighborhood. See, one thing that comes here is, if the function is something like this, x, y, and let's say if the function is maybe something like this, okay? And let's say this is the point x is equal to a, of course, x equal to a, then is it possible to draw a tangent here? First of all, if the function is discontinuous, if it is continuous, then whether it's differentiable or not we can check later by checking the limit. But first of all, if the function is discontinuous, can you draw a tangent there physically? Can you construct any tangent at that point x equal to a, exactly at x equal to a? So therefore, first of all, the function should be continuous if you want to draw a tangent, okay? So for limit to exist, the function need not be continuous, okay? Because without even having the continuity in the function, you can still show the limit exists, okay? Then for the function to be continuous, limit should definitely exist. For the function to be differentiable, then definitely it should be continuous first, okay? Then if it's continuous, then we'll check the limit is getting equal or not. Clear? So let's see, I'll work out one example and make the things much clear. See, this definition is same as this definition, okay? Because you can understand, maybe if I draw a graph here, you will see. I'll draw one graph to make you understand things in a better way. So if you have 0, x and y, okay, and you get this function, then let's see, if this is x, okay, or this is a, let's say, then ultimately this is f of a. And let's say if this is x, this is f of x. Clear? So x, f of x. So obviously dy by dx is nothing but f of x minus f of a divided by x minus a. That's what this difference. And if you want to converge towards a point, if you want to, for example, draw the tangent at this point, okay, if you want to draw tangent at this point a and want to discuss on stability, or sorry, and want to discuss on slope, okay, so let's say if you, maybe I'll draw a little slowly, okay, so if you draw a tangent here, then whenever you draw a tangent here at this point, well, I'm not satisfied with my accuracy, okay, so roughly fine, okay. So if you want to make this differentiation at this point, then ultimately this length should converge to this point, which means x should tend to a, or x minus a tends to 0, which is the same thing, okay. Now let us work out one example and decide whether this function is differentiable or not, okay. So let's see how we can do that. Is mod x differentiable? Is mod x differentiable at x is equal to 0? This is the question. Is mod x differentiable at x equal to 0, for example? Now ultimately, if you want to check whether at a particular point the function is differentiable or not, let's calculate limit x tends to 0, because I am interested at my point x equal to a, f of x minus f of a divided by x minus a. This is what we have, okay. We'll see whether this limit is existing or not. If this limit exists, then of course the function is differentiable. If this limit does not exist, then the function is not differentiable, okay. Then let's inquire. First of all, let us calculate the left hand derivative. Left hand derivative, okay. So when you calculate this left hand derivative, let's see, left hand derivative is equal to limit x tends to 0 minus mod x minus mod 0 by x minus 0. and anyhow mod 0 is 0, clearly this value is 0 straight away, so this is equal to limit x tends to 0 minus mod x divided by x, of course. Okay, now let's see in this case when x is tending to 0 minus. Okay, if x is tending to 0 minus, just a minute, okay, nothing, right? Yeah, pop-up is fine. So let's see, if x is tending to 0 minus, that means x is slightly less than 0. Okay, if x is slightly less than 0, this mod x is going to be minus x, correct? Because mod x is equal to minus x if x is negative. So when x is negative, this can be written as limit x tends to 0, mod x can be replaced with minus x. See, when I'm modifying the function, I'm not putting this minus again here, okay, on top of 0 by x. So x gets cancelled, this is equal to minus 1, because when you cancel this x and x, this is minus 1, of course, okay, and you cannot keep any limit because it's a constant, minus 1. Now when you come to the right hand derivative, let's see. Right hand derivatives are hd. For example, if you calculate this, then let's take it up. Okay, so our hd is equal to, right hand derivative is equal to limit x tends to 0 plus mod x minus mod 0 by x minus 0, of course. Okay, and this mod 0 is 0, clearly. Limit x tends to 0 plus mod x by x, this is what you get. Now clearly this x is tending to 0 plus, that means x is more than 0. So if x is more than 0, this mod x is equal to plus x. So limit x tends to 0, x by x, and clearly this gets cancelled, which is equal to 1. Now clearly you can understand one thing, this right hand derivative is 1 and left hand derivative is minus 1, so clearly these two are not equal. Okay, so since left hand derivative is not equal to right hand derivative, ultimately mod x is not differentiable at x is equal to 0. This is a very important statement, clear? So mod x is not differentiable at x equal to 0. Right hand derivative is 1, yeah, correct. Okay, so right hand derivative is 1, which you can see. Now we'll also see this later graphically in today's class itself, once I give you graphs. Okay, so we'll understand how we'll generate the graphs, but of course for mod x I'll just give you, okay fine, we'll discuss, okay, graphs we'll see graphically. But before this, I just want to ask you one question. The value of, you have understood the, okay fine, let's see the value of limit x tends to pi by 2 tan x. If I ask you this, what is the answer? So first option I'll give you is maybe minus infinity, b infinity, c 0, and d does not exist. The limit does not exist. That's what does not exist. Can someone comment on this? I'm conducting a poll. Okay, so 45 seconds is what I'm giving. Come on, answer. The value of limit x tends to pi by 2 tan x. I just want to calculate this. You can enter in the poll whatever you feel. Okay, quick, faster, only half an hour left. D, can be B, A, whatever you feel. Come on, time is running up fast. If you feel infinity, you click on A. Okay, poll is live. B, okay, B, okay. The correct answer for this is it actually does not exist. Okay, we'll see why it does not exist anyway. So Alex, yeah, correct. So we'll see why it does not exist. Of course, the reason for why it does not exist is since limit x tends to pi by 2 minus tan x is not equal to limit x tends to pi by 2 plus tan x. Okay, this is what it happens. We'll see. Now to know more points of this kind, okay, I'll again visit back differentiation and all, because I'll need to give some points on limits, continuity, hospital, all these things, but that may not be done in today's lecture. We'll revisit these concepts. Okay, but before we go today, we'll talk about some standard graphs. Okay, some standard graphs are important for some standard graphs. Okay, so let's see some standard graphs. And first of all, I want to tell you one thing. Why we say like if LHL not equal to RHL, limit does not exist, because when I tell you x tends to a, I can take x is lying in the left neighborhood and I can calculate the left hand limit, and maybe you can take the right hand limit and you should calculate. Whatever the ways we take, our answer should match definitely, correct? Because in the definition of limit we just told as x is tending to a, f of x should tend to L. We have never mentioned a direction. Okay, so if you take any direction, ultimately it should give the same value. Okay, so if it's not giving, then ultimately the definition is no more valid for that limit. Okay, clear to all of you? Now, before drawing graphs, I'll give you some general steps. Graphs. Okay, point 1. If, okay, first point you should do is check for maximum and minimum values of the function. Check for maximum or minimum values of the function. So first to check whether there is any limits. Okay, means is the function bounded between any two values? This is what you should check. Second, check for periodicity of the function. Periodicity of the function means basically, is the function repeating? Okay, is the function like you take sin x? Okay, sin repeats after every 2 pi interval. So similarly, if whether is there any checking, or basically is there any repeating kind of nature for the function? That's what you have to think. Okay, the limit does not exist. What does it physically mean? Actually, the system cannot take any value there. That's it. Okay, exactly. See, limit does not exist means when, let's say for example, if the function is running smooth and the signal is having some value, then suddenly there's an immediate jump and there's some, basically there could be some discontinuity. Okay, when you're turning in both different directions, the value will not be same. Like you might have drawn some diagrams. Okay, which branch are you from? Hi Krishnan, Rajmohan. Which department are you from? I just want to know so that I can give some relatable example. Okay, faster a bit. Mechanical. Okay, so you might have done shear force diagrams. Okay, SFD. When you're calculating shear force diagrams, you can find if this is x is equal to 0, then along the length of the beam, the shear force can suddenly drastically jump here. Okay, so which means you can see exactly at this point, generally we connect this using dotted line because we are not sure about the sudden jump. Okay, we connect this using dotted line, and till this part of the beam, the shear force value is this, and till this part, the shear force value is this. Exactly at this point, it's not known. Okay, so that's what it physically means. Clear? If limit is not existing, then ultimately there's a sudden jump or sudden change in properties. Like you have shock. Okay, in a fluid mechanics, let's say you have a shock, then ultimately there's a sudden jump of the properties across the shock. Okay, so in such cases, there's limit. Calculus fails. Of course. Yeah. Now let's see. Oh sorry. What happened? Okay, so let's see here. Periodicity. To note, I would like to give you some points. If f of x comma y is equal to f of minus x comma y, okay, then the curve is symmetric about y axis. It tells you that what are the values you get for x, that also is basically comes for minus x. Clear? yeah, transient but with a sudden jump. Okay, even see, if things are changing with time, of course they can be smoothly changing, but if there is a sudden jump in properties or sudden jump in the signal characteristics, then ultimately that's at that point limit does not exist. Okay, then second, if f of x comma y is equal to f of x comma minus y, then the curve is symmetric about x axis. Third, if f of x comma y is equal to f of y comma x, means even if you are swapping these variables, but if the function remains same. We have done this actually in linear algebra. We were solving one question. We got some equation 3x square plus 10xy plus 3y square is equal to 1, something like that. We have got one equation, or 9x, maybe 10x square plus 12xy plus 10y square equal to 1, I think, the ellipse equation. So we have seen in that equation, if you interchange x and y, the equation do not change. Okay, so then ultimately the curve is symmetric about the line x equal to y. X equal to y, of course. Okay, so x is equal to, about the line x is equal to y. Yeah, it should be symmetric about the line x is equal to y. Okay, so let us now, with this idea, let us start drawing some standard graphs. Which, let's start with the easiest ones, which you guys know. Y is equal to sin x. Okay, so if you plot this, then first of all let us follow the rules actually. So this, on this axis, xy axis, I want to plot y equal to sin x. Okay, so let's see y. Then first point, check for maximum and minimum values, if any. Okay, so then let's see. Ultimately, you know, -1 is less than or equal to sin x less than or equal to 1. Whatever you keep in place of x, it always comes between -1 and 1. So first of all, bound the limits. Okay, so let's say this is x is equal to, sorry, y equal to 1, sin x is equal to 1, and this is y equal to -1, of course. Okay, y equal to -1. So that we can clear now. Okay, so let's say we have done it like this clearly. Now let's see. Next, second thing, look for periodicity. Why? How do you look for periodicity? Is the function repeating? Yes, every 2 pi intervals it repeat. So let's say if I plot it from minus pi to pi, for example. Okay, so this is minus pi. So let's say this is pi. Clear? Then from 0 to pi, you know, the graph of sin x, you can basically plot it. So it goes to pi by 2 and comes here, and similarly okay, so see, okay, so this is how you have the sin x graph, of course. Okay, so this is y equal to sin x, and this, since it is periodic, this loop keeps repeating. That's it. Okay, so this is how you have the graph of y equal to sin x. In fact, this is minus pi by 2 0, then you have pi by 2, of course, and this is pi clearly. Okay, that's what you have. Similarly, you can do for cos x with a phase change of pi by 2. Let's see, I'll draw for y equal to tan x, because cos x, you know, just you shift it by 90, then you'll have a phase difference of 90 could actually give cos x. So y equal to tan x. Okay, so let's say we get y equal to tan x. Then how do we get for tan x? Let's see. You'll also understand why limit does not exist. So this is x and y axis, of course. Okay, then 0 x y. So first of all, is there any limits for tan x? No, obviously tan goes from minus infinity to infinity, so there is no bounding. Like in this case, this is y is equal to 1, this is y is equal to -1, 1. Okay, now let's see if this is xy, then let's check for periodicity. Yes, tan is periodic. If this is minus pi by 2 and if this is pi by 2, then again you have things like pi, then 3 pi by 2, of course. Okay, and here you have minus pi, of course, pi, and minus 3 pi by 2. So let's say you have this thing. So ultimately this value is minus pi by 2, then this is pi by 2, 3 pi by 2, pi. Okay, so sorry, pi by 2, pi. Okay, so this is pi, of course, pi, and 3 pi by 2. Similarly here you can check minus pi, minus 3 pi by 2. Now if you plot the graph of tan x, then again tan is repeating, of course. So clearly this value will be, this is how you get a graph. It's asymptotic almost. Okay, so you see maybe it never touches, but it's because you cannot plot infinity physically. So similarly here this will be repetition. Similarly here starts at this point and it comes up like this. So this is the graph of tan x. Now you can clearly understand, limit x tends to pi by 2, tan x, this fellow does not exist. This does not exist. The reason why this does not exist, because if you take x equal to pi by 2, this point, okay, then in the left neighborhood the value of the function is plus infinity, in the right neighborhood the value of the function is minus infinity. Clearly there is a break, and of course even though it is discontinuous, at the same time the limit value is also not equal, because both sides give you two different values. Okay, when value of x is in the left neighborhood, this is when means when it's slightly less than x, the value of the function is plus infinity, the green color graph is in plus infinity. But when it is slightly more than pi by 2, it is coming to plus minus infinity. So therefore, since limit x tends to pi by 2 minus tan x is not equal to x tends to pi by 2 plus tan x, of course. Okay, this is what. Yeah, which means function does not exist at that point. Yeah, of course. See, function may or may not exist. That's what I'm telling you. For the limit to exist, function may or may not exist, doesn't matter. Okay, the function should oppose that value. That's it. Exactly at that point, function need not have a value. Okay, but even though both the sides are not converging to the same value, then we say limit does not exist. Okay, like here you can see. Okay, is this clear to all of you? Yeah, fine. Hello, we'll give you one more graph today. Y is equal to log x to the base a. Okay, y is equal to log x to the base a. This graph has one very importance. The reason is the graph shape is different if depending on value of a. For 0 less than a less than 1 and for a greater than 1, and you know log is not defined for a equal to 1, so this a is not equal to 1. Now if you plot for these two different values, you clearly know log is not defined for negative values of x, clearly. Horizon x y, when 0 is less than a less than 1, the graph comes something like this. Okay, it goes to infinity, of course, and this is y equal to log x to the base a if 0 less than a less than 1. Okay, and if you look for something a greater than 1, then let's see. origin x, y. It starts from minus infinity and it goes like this. Okay, in both the cases you can observe this value is 1. Okay, so this value is x is equal to 1, and this is the graph. It keeps going. Okay, y equal to log x the base a if a is greater than 1. Clear? These are the two graphs. Many times people don't know. So what's the difference between function and limit not existing at a point? Can you please explain? So I didn't get you. Function, what is the difference between function? See, function value means exactly when I put x equal to 2, exactly. Okay, exactly when I put x equal to some number, the function should have some value. Like you say f of x equal to 1 by x minus 2. When I put exactly x equal to 2, the function is not defined. Okay, then you see function value does not exist at that point. Okay, but limit can exist. Okay, that's how. Clear? See, simple example na? I have drawn in the first slide. When I'm teaching the concept of limit, here you see this limit is existing here because as x is moving towards a, this function is moving towards L. But clearly at exactly at x equal to a, this function don't have any value. Got it? That's the difference. Clear? Yes or no? Is this clear to all of you? Got it? Anyway, I think it's slightly concept heavy today, correct? We are dealing with a lot of graphs and all. So we'll do one thing. Okay, we'll stop this class here because I know it's getting to be conceptually slightly hectic because we have started everything in terms of geometric point of view, then differential, all these things. Okay, so we'll stop this lecture till this point because I think conceptually it's getting heavy, of course. Okay, then anyway, there's few more graphs. We'll try tomorrow. We'll continue the graphs tomorrow. Okay. We'll basically draw the graph of some complicated functions like x into sin x by x. We'll draw all these things. Sin x by x, what are the specialties, mod x. We'll discuss these kind of graphs. Then we will look into the concepts of derivatives. I'll give you some standard derivative formulas, and then we'll apply L'Hospital rules, and then we'll go back deep into the limits. Okay, that's how we'll progress tomorrow's class. So maybe today I'll stop here. If you're interested, you can actually solve one question for homework if you know L'Hospital rule. Anyway, I'll just give you some homework, which I think some basic questions you can do. This is your homework. Then this is also you can know. Okay, fine. With this will be slightly hectic. Yeah, this you can do. This okay, we'll deal in tomorrow's class. Okay, fine. That's okay. 2 questions I given you for homework. So please try this. Okay. Is auto rotate in a phone as an example of rotation matrix? Yeah, it rotates by 90 degrees, of course. Okay, but practically it doesn't shift the coordinate system. It just keeps whatever you're seeing in the same form. Okay, it doesn't rotate the image. Clear? So you cannot perform your rotation matrix basically for the rotation in your phone. Okay, because if you're rotating your phone, the complete image is getting rotated by exactly that platform. But it's not the it's fitting to the skin, but it's not the rotation that's taking place. Okay, by the time you rotate your phone, it's not like your image is tilted. Clear? You're getting the same image but in a larger scale. So anyway, so today basically we have talked about the concept of limits. Then we have also discussed about continuity, the concept of continuity. Please go through these things. Okay, these are nice graphical insights which you can understand. Then this is differentiation. Okay, so these are the things we have discussed. In fact, I thought of dealing more, but again conceptually it's I understand it's the first class of calculus. To from Venice. Okay, so it takes some time. Clear? So does that jump mean an unstable system, a chaotic system? You figure it out. Okay, well, you do some study on this, you can find it out. Good. Okay, because when you say the word unstable, it means lot. Okay, it can be understood in different senses. Well, so well, anyway, so we have stopped here because I think it's slightly concept heavy till now. It stopped. So again, we'll meet tomorrow at 7 PM. So we'll continue the graphs. Basically, I'll give you some more graphs, and then we'll do things on L'Hospital rule, and we'll see much more insights of continuity and differentiability. Okay, when one function is when one limit is not existing, but if another limit is existing, and if these two are multiplied, then what happens? Okay, these things clear. Yeah, I'm going to cover all these things. Okay, DICS, all this syllabus. So anyway, thank you all. We'll meet. I have given 2 homework questions, so please work out these 2 questions tomorrow. by tomorrow, then again tomorrow we'll start the class. Okay, yeah, fine then. Any questions, quick questions that you can ask, or else it's fine, we'll wind up. Ashwant, basically in the link in the description there's a link. Okay, so if you click that, you can find these notes whatever I'm writing in the class, so in that itself you can find the questions. Okay, yeah. Other concepts, yeah, we have many more lectures. Okay, today is not the last lecture of calculus, please be patient, we'll cover. Okay, fine. So thank you all, we'll meet tomorrow then. Okay, at 7 PM sharp, please be on time, then we'll start the things, we'll continue the things. Okay, yeah, fine.